is Kara Baylog. I'm with the Shasta Valley Resource Conservation District, the watershed coordinator. Welcome to tonight's presentation. This is our second workshop of our fall lineup for the Siskiyou Forest Stewardship Workshops. Tonight we'll be discussing climate change in Siskiyou County, what we can expect to see, what we're already seeing now, and what we're doing about it. The Siskiyou Forest Stewardship Workshops are hosted and sponsored by the Shasta Valley RCD with support from the Siskiyou Land Trust and the Natural Resource Conservation Service. It's a monthly series of talks we put on, bringing local and regional experts on various topics in forestry to our communities to help us make our decisions in forest management. We posted topics ranging from community forestry to meta restoration to defensible space to prescribed fire. Videos of this, the past and future workshops can be found at our website at www.svrcd.org under Rainbow Ridge. I do also want to invite you to sign up for our mailing list if you're interested in finding out about future workshops we put on. It's just right up there. We send you a monthly email about our workshop. I promise you no further spam than that. So let's get into our workshops. So we're going to start off here. We have three excellent presenters. We're going to start off with Carl Skinner. Carl Skinner is a recently retired research geographer and science team leader in the Fires and Fuels program at the Forest Service Pacific Southwest Research Station. He has a degree from Shasta College, UC Berkeley, and Chico State University. Carl grew up in a farm in eastern Shasta County near Boerne, and he began working with the Forest Service in 1968 in fire suppression on the Hat Creek Ranger District in the Alaska National Forest. He worked on the Mount Shasta Ranger District in fuels management and prescribed fire from 1980 to 88, and then he transferred to the Pacific Southwest Research Station in Redding in 88 to do research in fire ecology and management. His previous research with the Pacific Southwest Research Station focused on how to understand fire, climate, and management activities, and how they interact to influence forest vegetation dynamics and fire hazard. He currently lives in Portland, and they have 3 grown children and 3 grandchildren. So I want to invite Carl up.
Thank you. Well, this is always one of my favorite places to come because we did live here for a while, and I love this area. And so it's nice to be asked back to be able to give a talk here. And let's see, how do I go forward? Oh, okay. And so they asked me to talk about climate change and what we might expect, and I'm supposed to be setting the stage for a couple of talks that are coming after me. And there we go. I got it. So what I wanted to start off with is the evidence that, yeah, we are seeing climate change. And this is what we're seeing from 1850 through to the current time in terms of relative change. And annual averages, you can see it's kind of up and down from year to year, but the trends are up. And this is decadal trends down here, where you kind of average it over the decades, and you can see what's happening in the last several decades. This is essentially worldwide. Average is what you're looking at here. And this is from the IPCC report that was just put out this last year. So it shows that that is indeed what's going on. And if you look at it over a longer period of time, this is the last 1,000 years, reconstructed from tree rings. And this line that's right here, that's 0, the baseline, that's the average temperature for the period from 1960 to 1990. And so what you see is for over the last 1,000 years, the temperature has generally been much cooler than what we are experiencing now, and then all of a sudden that period on the end there, that's what we were just looking at in that other chart. Look at how fast it's happening. This is what's called the hockey stick graph. It's kind of shaped like a hockey stick. And but it shows that that's how fast temperature is rising, and that's what's really unusual about the time period that we're in. So climate change is real, it's happening, and there's some people that say it isn't, but who knows. Here's what's happened from 1901 to 2012 in terms of how temperatures have changed across the Earth. And if you look at the redder or deeper purple it is, the more warmth that there is compared to what there was at the beginning of the 20th century. Now you do see a couple of the white areas are areas without data. But you do see some places with a little bit of blue up there, like just south of Greenland in the North Atlantic is a blue area. Any idea why that is?
Cold water.
It's because there's a whole lot of cold water there because of the melting of the Greenland ice sheet, dumping all that cold water into the North Atlantic. And that's going to play havoc with the weather of Europe for a while, and has been over the last few years. In fact, a colleague that I work with actually published a paper that says that that is what actually turned around the global warming that began during the medieval period, was that happening in the North Atlantic. Well, right now, though, things are going so strongly that it's probably not going to make that much of a difference. So what's happening in terms of climate change? Mostly temperature, that's what we know that it's warming. But what's interesting is how it's warming. What we're finding is that night is warming more dramatically than daytime temperatures. Daytime temperatures really haven't changed a lot. Nighttime temperatures worldwide are what are really warming. And what that's doing is it's bringing the average temperatures up. And it's meaning that you're not getting as much cooling, and even in the winter time you don't get as much frost and frozen conditions and so forth. It's changing environments tremendously. The other thing is that winters are actually what are warming more than summer. Summers haven't warmed nearly as much as winter conditions have worldwide. Elevation, the other thing that's happening there is that higher elevations are warming faster than lower elevations. Most people live at the lower elevations, and so people haven't noticed it as much in that sense as say folks that might live up in the Himalayas, that kind of thing, because high elevations are warming much faster, and that's one of the reasons that the glaciers are almost gone in the Andes now. They in the last 20 years, and so forth, and other areas. And then latitude is interesting. The poles are warming faster than the equatorial regions. And if you look at all of this, what it means is those places that used to be the colder places are the places that are warming the fastest. And the warm places aren't so much. And the reason that that is just the Earth is trying to balance out all this heat that it's receiving. And that's where it seems to be going, is into the cold, changing the colder conditions and such. So that's kind of the pattern that we're seeing worldwide, is this is happening. Now, in terms of controls on fire, I got to say some stuff about fire. Controls on fire, what controls fire in any particular environment? And the research that we've done indicates to us climate is the #1 controller on what the fire activity you have is and what the fires are likely to do. Next to that is the geology that you have, and that's basically what creates the soils and the conditions for stuff to grow in, and so that leads to productivity, how much fuel can actually be there. And then topography influences it a lot. These are all physical things, is what we're seeing are the main controllers on fire. Vegetation, which is what we actually see burn, is not as much of a controller on fire regimes as these other things are, because vegetation is actually responding to all of those as well. And this leads us to some very not always obvious conclusions about things. One of the things that we know, though, is that we have a Mediterranean climate here in California and in southern Oregon. And basically, the Mediterranean climate means that we have cool, wet winters, normally, and which grow lots of stuff, vegetation, fuel, and but we always have a warm, dry summer. And we have an annual fire season. That's not necessarily the case everywhere. We have fire season every year, and we have stuff that even if people aren't setting fires, we're going to have fires anyway. So that's a Mediterranean climate. And all of the modeling that's been done in terms of climate change and where we might be headed into the future, this doesn't change. How hot it's going to be getting at different times of the year, how much precipitation might come during the wet season, that kind of stuff might vary with climate change. But where we sit globally in terms of latitude and such, we're still most likely going to have a Mediterranean climate. this kind of a pattern. And there's what it looks like in terms of rainfall. If you look, there's Cave Junction, Appicamp, Orleans, Dunsmuir. Most of the precip comes in the cool part of the year, and you don't get much when it's hot. And because of that, we're set up to burn. And and as things warm, there's stuff happening to this pattern as well. That's kind of interesting. But the other thing we have here is lightning that can set it off. And now these are, the red dots are lightning-caused fires, and the blue dots are human-caused fires. You know, you hear the only you can prevent forest fires and humans cause most of the fires. Well, look at that map. This is a 10-year period from 1986 to 96. And what it shows us is, yeah, you get a lot of fires where there's lots of people. But when you get into the mountains, where you get more thunderstorms and such, lightning overwhelms what you get in terms of the amount of fire activity. And so you can see that, and you can see where we are out there in northwestern California, Northern California, that lightning is definitely the major player. We all, those that have been here very long know that, but it is definitely borne out when you see maps like this. And in northwestern California from 1987 to 2008, 1.6 million acres have burned in that period, and 87% of that is from lightning-caused fires, not human-caused fires. And this is something that is counterintuitive. One of those things that until you look at the data, people think all kinds of stuff. And we think, okay, we have lots of lightning strikes, we're going to get lots of fires. What we're finding, what we see is those years in which we get the least amount of lightning strikes are when we get the most area burned by lightning fires. And it's, in fact, if you look at it, this is 1987, right here. This is the amount of lightning strikes in northwestern California. And this is, over here, was 1999. Big, both very big fire years. And look at this. These years, we hardly had any fires. And what it is the years when you get the most lightning strikes are the years when you have the wet thunderstorms. That's when you get a lot of wet thunderstorm activity coming through, and it keeps the lid on the fires, and the fire crews can get there in time to deal with them. The years that are like this are usually when they're very dry, and you only have 1 or 2 thunderstorms come through in the summer. But everything is dry like this year, and you get a day like this. Those are lightning strikes in June 21st, 2008, and it's very dry, almost no rain with the lightning, and it overwhelms the suppression forces. And so that's why you get lots of acres burned in those kind of years. And this is what happened that year in terms of water. The blue here, this is Redding, the normal monthly rainfall. This is actually in millimeters, but I put the inches over here. And you can see what the normal is. The yellow is what happened in 2008. You can see it almost shut off here in March. Dropped way down in February and almost shut off in March. And that's basically what happened. And that's what we're seeing more and more actually with global warming, is this kind of a pattern. In those years that are dry, things are shutting off earlier. The fire season is getting longer. Now, we've done fire history studies all over the place, and those are some of the tree ring studies we've done. Myself, Alan Taylor at Penn State, Scott Stevens at UC Berkeley, and Valerie Truitt at University of Arizona. We've all been cooperating on this stuff. And then I worked also with Kathy Whitlock at the Montana State University and Christy Browse at the University of Colorado. And we've cored lakes all over the area and looked at actually long-term charcoal patterns and such in the lakes. And I'm not going to go into all the details about this, but one of the things that's really interesting is that we found, and I've given talks about this before, how frequent the fires used to be. There used to be just fires all the time. And smoky skies in the summer was typical, and it's interesting to think that most of that covers the period of 1600 to 1900, the tree ring period, that we have frequent fires. And that is in that period, which I already showed you this graph, cold compared to today. That was a very cool period, and yet there was still all kinds of fire going on then. Shorter fire seasons, cooler temperatures and that, and lots of fire. And now we're on the upswing in terms of temperature and longer fire seasons. So, one of the things it's taught me is that climate is always changing. There is no normal. But sometimes it changes faster than others. And right now is one of those times that it's going really fast compared to anything we had record of in the past. The only times that we've seen climates change as rapidly in the past, as we're seeing them change today, is when they cool, not when they warm. The warming seems to have, in the past, always taken a much longer period. But cooling, not necessarily, because various things can cause that. So fire and climate change, where are we headed? What we're seeing is that fire season's getting longer. The fire season in the Western United States, just since 1970, just in the last 30 years, I'll put it that way, 30 to 40 years, has increased by an average of 70 days, west-wide. And that's the fire season that starts in West Texas, New Mexico, moves up through the Rockies and ends in Southern California. That period is taking 70 days longer now than it did in the late 1970s. So fire season is getting longer, we know that. Vegetation keeps growing up. And this combined gives us a probability, a greater potential for intense fires, unless something is done to deal with the vegetation. Now here's something I want to bring up. These are models suggesting how much change there might be in surface temperature compared to the last couple of decades of the 20th century and the end of this particular century. And this is one model that says, well, we actually do a pretty good job at dealing with carbon and the other things in the atmosphere. And we know that there's still, even if we quit pumping carbon into the atmosphere today, there's 70 years worth of warming in there. It's a lag in terms of how much gases are already in the atmosphere. But and so that's this one. And that shows some warming and so forth, but not as bad. And this is the one over here that if we don't do a good job of it, and we just kind of keep going down the track we're already on, that's where we're going to end up, is that way. A much warmer and a very different world. And you can see the precipitation patterns change as well. So the reason I bring this up is that just yesterday, and I didn't get a chance to put any of it in here, a report was released by the Pricewaterhouse Group, which is a huge accounting firm that the big corporations use. And they wanted them to assess what the potential effects of climate change might be. And a lot of these people are people that are deniers even, not the particular accounting group, but the people that are their consultants, the people that consult with. And this report's a 20-page report, and they said basically when they crunch all the numbers and they look at everything that's going on in terms of the data, and what the models are saying is that, there's these ranges of models, and they said that that's the one we're on. That we have not in the last 10, 15 years made any appreciable difference worldwide with a little bit of trying adjustments we've been doing. So what does that mean for Northern California? This comes from NOAA's Geophysical Fluids Laboratory, and these are December, January, February, and this is June, July, August. And just kind of shows temperature ranges that you can expect. And then this is how it changes by the end of the century according to these models. You can see a whole lot more red in there, and not so much green up around the Shasta area and such. And this is the amount of warming, and this is all in degrees centigrade. So you can almost double that and figure what kind of temperature Fahrenheit is going to change. So that's kind of what we have in store for this, according to the models. So this always comes up. Hasn't climate changed before? Never when accompanied by 50 to 100 years of fire suppression. Saving up food. That's never happened before, no matter what climate ever did. Because fires were always able to adjust as the climate was changing before. And this time we tried to change that. So, climate change and fire regimes. Climate variation. How is climate variation likely to affect fire activity? What we have found is that temperature affects fire frequency. The warmer the temperature gets, the longer the summers are, and the drier things get towards the end of summer, so you're more likely to have a fire in any given year. And so you more often have fires, is what the tree rings tell us. But moisture, the more moisture you get, determines how big the fires get and how severe they are. Because we always have those dry summers. And so the more moisture you get, the more stuff it grows. And the more fuel there is there then to feed the fires. So fire, we believe, is looking at the long-term charcoal stuff and pollen from the lakes. Fire is the major catalyst for changing of the environments when climates do change. That trees have an amazing ability to withstand a lot of temperature variation and precipitation variation and stuff. So once they're established, seedlings are a little more sensitive and such, but once trees are established, the forest can hang in there for a long time until a severe fire comes along. And so we believe, even in cases, here you have lots of options as to what you might be able to do in the future. There, not so many, but still a lot of options actually. And but when you get something like this that happens and burns huge areas and changes the landscape, now you've got a major change. You don't have seed sources anymore. And then even if some seedlings are trying to grow in there, that you have to keeping fire out of there, which we weren't successful with to begin with, for another 100 years until those trees are large enough to be able to withstand whatever the next fire might be, has become really problematic. And so essentially what we've done in many places like this, and we're doing it more and more, is we're causing a lot of vegetation shift. We're changing from one vegetation type to another with climate change, and then without significant help, the places like this are unlikely to make their way back to forest, at least not anytime soon. Now this is something new. I hope I have enough time. This is a study we just did in the Lake Tahoe Basin. We did it there because they were selling a whole lot during the land booms and stuff, the housing booms and all that. There was all this land around Las Vegas that was BLM land. And some Congress people decided, well, why don't we sell it off and make some money? And so they sold a bunch of it off, and then the senator said, well, then why don't we actually, instead of just blowing all that money on stuff, let's put some of it into research. And so they said, okay, we'll give it to the Tahoe Basin and we'll have them do research. And so that's why we were able to do this study, because we got some of that money. And what we were looking at, these are the fires in the Tahoe Basin. There haven't been a lot over the last 100 years. And most of them are small. There's a couple of big ones you've heard of. And so we wanted to see what climate change was likely to do in the Tahoe Basin with fire. Because fire hasn't been that really big of a player there, and because of the elevation and the snow that they get and stuff. And so here's, we also used the plan that they have in the basin for fuels treatments, defensible space, and that kind of stuff to see, okay, if they build this out, does it make a difference? Or does it not make a difference in terms of what climate change is going to do? And that. And so we put all this in models. We got a number of really good models together to do this. Louise Loudermill and Rob Scheller at Portland State University, and Peter Weisberg and John Yang at University of Mount Reno. I mean, they've built some of the most intricate models that these people use to be able to look at this kind of stuff. And so we actually were able to get them to focus on this area. And some of what I'm going to show you isn't actually published yet. Most of it is, but some of it is in review right now. And so what we looked at was ignitions. How much ignitions are? This is the current pattern of ignitions for the last 30 years in the Tahoe Basin. And so red means a whole lot of stuff, and this is where most of the people are. And then the green is not so much. And so that's the pattern. Here's the human ignition pattern. And there's lightning. And you can see lightning is hardly anything. There's a bump over there, and I think that's not road. And then, but you can see this is the pattern. So what we wanted to do is what's going to happen with the ignition pattern that's down the road. And so we looked at the different climate models. This is B1. That's the one that is the best case. That if we do a good job, this is what's going to happen, the models say, to the ignition patterns in the Tahoe Basin. Here's the worst case. It gets pretty heavy. And what's interesting to us, what was interesting to us, is what makes the difference is lightning. It isn't the human-caused stuff, it's the lightning that is making a difference. And the reason that it makes a difference is that, and it spreads it all over the place, is because lighting doesn't happen just where people are, it's happening all over the landscape. And lightning-caused fires in the Tahoe Basin ended up being very strongly predicted by January snowpack. And so the less snowpack that they develop there, that means the earlier the spring, the earlier drying of the fuels, and it makes it more susceptible to lightning fires. And so even without more lightning storms, without more anything, if you just give it the same number of storms we've had in the past, lightning takes over and spreads fire all over the basin by the end of the century. Which was really, we weren't expecting that at all. That was very unusual. And that's the one that's in review right now, hasn't been published yet. Big it up. Early view of it. The other thing that we did, and this one is also not published yet, the next slide I'll show you, is we looked at, okay, let's build out their thing. And we'll say the climate just stays the same as it was in the mid-20th century for the next 100 years. What difference does it make? And so what we found was really interesting. It didn't make any difference what they did. They could build their fuels plant, they could not, whatever. They didn't get enough fire under the average conditions in the 20th century to make a difference in the Tahoe Basin. Even when we added in bark beetles, with that climate, by the end of the century, everything just kind of comes back together, and this is differences in the amount of carbon stored in the trees in the basin. And what you notice is it's on an upswing all the way through. The reason for that is the Tahoe Basin was whacked during the mining period. They took everything out. And so it's all regrowing. So even if you have a lot of stuff happening to those trees along the way, they're still fairly young trees growing and putting on carbon. And so that was the other thing that was kind of surprising to us that we saw in the Tahoe Basin. Okay, now let's do the A2 climate. And see what happens. Here's what goes on. Look at how it drops, even though the trees are still growing. If you just do fire alone, modeling, or if you do the harvest and fire, it's growing, but it's not doing as well. The trees are stressed, they can't grow as well as they were before with the warm climate and that kind of stuff. But when you add needles in, look what happens. It crashes.
And Carl, the A2 model is what?
What's that?
The A2 model is which?
That's essentially the model that projects out where we're actually headed currently. That's almost the worst case scenario kind of a model. And but that's the one we're on right now, unless we change something. It's essentially what it is. And what's interesting about it is that you see what the beetles do in terms. This is above ground. This is total carbon. Is what you're seeing. Is the difference between the upper one and the lower. And so the trees really take a hit. Is what's happening when we add beetles into the models as to what's going on, and that's because of these stressed trees. And what climate is doing to the trees and making it more difficult for them to grow, and then the beetles are able to run amok, even with doing beetles and fire. But harvest and stuff, that part of it, the beetles are the ones that are overwhelming the whole equation, which we weren't expecting to see that at all. But we added them in just because, well, dealt with fire and we didn't see anything really interesting. Let's see what's going to happen when we add beetles in. So we brought another researcher in, Matt Hertow. He's at Penn State, who's done a lot of work with modeling beetle stuff. And that's what happens when you put that in. And so it really makes a difference. And the reason that there's a difference between above ground and total is that what you're seeing is that when you get major events happen, you're getting a shift to shrubs instead of trees. And so you still have a lot of below ground stuff going on. It's just above ground is changing. The formulas. So, where are we headed? Like I said, fire seasons are getting longer. Vegetation keeps growing. And we still have that greater probability of intense fires with the situation that climate change is working. And these are all people involved. So, I want to thank you.
Quick question before we move on to the next speaker.
In the beginning, you showed us the timeline from the medieval times up till now. And I'm wondering if there are any parallels, like when the fire in seasons, when the dips and the valleys and the highs in the olden times changed. Is there any, how did they change? I know did they figure out what made it change, if it was going way, way up or way, way down?
Yeah, that's some of what we looked at. And what we found is that in the past, without fire suppression involved, when you got warming temperatures, you would get more frequent fires. The fires would come more often in any particular place you look as the temperatures increase. And, but what would happen is that if you were going into a warm, dry period, the fires would burn up the fuel in the first few years, and then they become small and very limited as to what they could do because there wasn't a lot of fuel there. And it was only if you had warming temperatures with more precipitation that you got more expansive fires on a regular basis. But we did see those kinds of things happen. Whenever things warm up, you get more fires. When it cools down, you get fewer fires. And that goes as far back as we can see. And and we don't see where fires, except in very few cases, really make those big shifts in the past, such as the kind of shifts we see going on so much today.
Do they affect the climate, the fire?
Well, the fires are going on all the time now. So they do affect the climate in the sense that they have always, ever since there's been vegetation that can burn on the earth, whenever you have fires, it releases carbon. That's always been the case. So in one sense, that's background. That should not be considered in terms of what is causing global warming. Global warming is the stuff in addition to the background. And that stuff that's in addition to the background is the stuff that humans are doing today.
The one thing I didn't see in any of your charts was the difference between unmanaged and managed forests. And we can manage for fire, we can manage for warming conditions, but it's hard to manage on smaller acreages in California when the rules are so complex that those people that own less than 100 to 160 acres are locked out of management because they can't afford to do the planting.
No, I understand. There's a lot more to this, and there's a publication that should be coming out any time. We just finished it. It's a big synthesis of science of the last 15, 20 years for the next round of the National Forest to use for their land management plans. But we have a lot of stuff in there about fire and the influence of climate change on fire and the kinds of tactics or so forth, or at least strategies that we believe would be successful at moderating what climate change can do. And you probably haven't seen my other talks. I usually get into more detail on that kind of stuff, but I don't have the time tonight.
It's the policymakers is who you get.
Yes, the policymakers and the politicians. Yeah.
Okay, one more and then we'll do more questions after.
I understand, however, that if you have good canopy, that it cools, that the soil, the stuff below stays cooler. And if you take away the canopy, then the soil gets hotter. And
We actually did a study right on the north side of Mount Shasta. in the Goose Nest Ranger District on that very question. And it had to do with how much difference does it make in terms of fuel moisture if you leave the whole canopy or if you thin it. And what we found is that the ground fuels do tend to dry out faster in the open places. But by the time you reach mid-July in our long dry summer, they've come together. And they stay together until you get the first rains. There's no difference in terms of the amount of moisture because our summers are so dry. It just wrings everything out.
Hope you can hold your questions. If you have any more for Carl after, then we'll do them after. Next up, I'd like to welcome up Catherine Fitzgerald. She's with the U.S. Fish and Wildlife Service in Wairika, where she works closely with the Klamath and Shasta Trinity National Forests to conserve threatened and endangered species. She got her PhD from Stanford University, where she studied invasive ants. Her previous work has included work with the Forest Service, doing surveys on marbled murex at sea, and another survey on breeding rust-resistant sugar pine, among many other things. So, come on.
Hi. So this slide is a little bit of a bait and switch. You just heard that I work a lot with threatened and endangered species, and everybody knows the polar bear is, it's having problems due to climate change and all its ice is melting and everything. I'm not going to talk about polar bears or other kinds of threatened and endangered species today. I'm going to talk more about, instead of using big, giant examples that happen someplace else, I'm going to talk more about what kinds of things we see overall, and I'm going to try and talk as much as I can about what we know about what's going to happen generally in Northern California. So there are some things that we can predict, especially at these large global scales. But there are some things, when it comes to wildlife, there are some things that we know for sure are going to throw us for a loop when it comes to climate change. So I'll say what some of those are. But there's a lot that's already happening. There's research that's been done over the past 100 years, 20 years. And as you just saw in Carl's talk, climate change has been going on during that period. So by looking at that, we can see what's happened so far and maybe think about how that's going to continue into the future. And I want to say a lot of my slides have a lot of information on them. Don't try to read all the words. So the big picture, we're going to see a lot of species moving their ranges north or moving their ranges upslope if they live in the mountains. So here's a map showing how migratory birds are spending the winter farther north. And this is just a schematic over here showing some different ways that it might happen for a species that lives on a mountain to move upslope. And I want to just say, when I say farther north, I'm only talking about the northern hemisphere. So if anyone here is from Australia or South America, I apologize because I'm just going to use north in here as a synonym for poleward. Right now we're in the northern hemisphere, and north is the direction that a lot of species are going to go. But it would be different if you lived in Australia or South America. The species would be moving south. But so when a species shifts its range to the north or upslope, it's not clear what that's going to mean all the time. So you could have a species that shifts just the top part of its range upslope, but the bottom stays the same. So that species now has a bigger range. That species is winning under climate change. Good for it. But other species might just shift the lower part of their range upslope, and the top part might stay the same. That species just lost a bunch of its range, didn't gain anything, and that species is probably having a hard time. So a lot of how we figure this out for an individual species is based on this idea of the climate envelope, or the niche. And niche is actually a much bigger concept. I'll get to that in a minute. But just a very simple one, just thinking about the climate envelope. Say we have temperature and precipitation. And of course, climate can include all of the things that Carl was just talking about. the temperature and precipitation, two really easy things to think about. And let's say this blue block here just shows the area, the temperature and the precipitation in the area where the species lives. We can go out and see where the species lives now. Where can you find it? Write down the temperature and humidity, or temperature and precipitation, and it'll all fall into this blue blob when you put it on the graph. And you can take that and you can say, okay, where are all the places that have a climate like that? And the dark blue on this map show places where climate is really a lot like that, and you really expect to find that species there. Greens are a maybe, and this beige color is, no, you're not going to find that species there. The climate is too different. It's like this, or it's like this. You're not going to find that species there. And then you can look at all those climate models, and you can say, well, in the future, this is the place that's going to have the appropriate climate for this bird. So this is the evening grosbeak, and this comes from Point Reyes Bird Observatory. If you want to mess around with it on your own, this is the URL. But you can go through and look at all kinds of California birds, and you can zoom in on whatever area you're interested in California to see what they predict for the future distribution. And one thing to note about these are not like the Sibley Guide range maps or anything like that, which are actually a map of where you find the species for real. This is a map of places that have the appropriate climate. So they might not be there. There might be some other reason why they're not there. Or they might be there, they might be over here, and those birds are just for some reason able to hang on in that area. There's something else there that's good for them. They have a little broader environmental tolerance there. So there are a lot of other things besides the climate conditions that go into where you find a species or not. And that's actually, the niche is all of the things that make up whether a species can live there or not. One of those things has to do with other species. So let's just say, two species. Here's the one we were just thinking about. And by the way, this blob has nothing to do with that map that I showed you. It's completely hypothetical. And it doesn't have anything to do with this map either. Let's say here's another species that likes a warmer temperature and doesn't care about precipitation. And so if you are in one spot here, and the climate warms, well, now you might have two species living there, assuming that both species can move and get there. You might have two species living there, where before you only had one species. Maybe these two species don't really get along. Maybe the red one outcompetes the blue one, and so you just have a completely different species now. Maybe you like the blue one. You'd be kind of sad that it's gone. So in this situation, over here, this is a map that I stole from somebody else's research, like many of the maps you'll see. If you want to know where you can get them, you can look down here, but don't try to read all the words unless you really want to look it up. So this is showing currently where you can find, let's see, this is the wren-tit in red, and in blue is the rufous crown sparrow. And that's where you can find them currently, and they don't overlap too much. But in the future, under the climate models, this is where we're thinking you can find them, and there's a whole lot of overlap here. Are they going to get along or not? Are they going to be able to live together? Are they going to be competing a lot for resources? We don't know. And so one of the things to think about when I say we don't know, a lot of the climate conditions we're going to be seeing in the future. So these maps here just show climate conditions, nothing about species. But the red on these maps show climate conditions, combinations of different climate variables that we've never seen before. So this has kind of a science fiction name, no analog future. Novel combinations of climate conditions, and makes it, first of all, hard to predict whether a given species is going to like it in that climate condition or not. But even if we could, it's going to lead to novel combinations of species. So these are two completely different studies done by different people, but they each showed that in each of these maps, the red areas are areas where the group of species that's going to be living there in the future, according to all of these climate models, is completely different from any group of species that each of these species lives somewhere now, but they don't all live together. And you can see if Northern California kind of pops out in red, each A, B, C, and D are all different climate models, different scenarios, and different ways of thinking about how the climate works. But no matter what climate model you use, and these two studies use different measures of how similar groups of bird species were to other groups of bird species, you still see that Northern California has some spots where we're going to be seeing these really different groupings of species, and we just don't know what's going to happen when we get those different groups together. So there are a lot of other things to think about besides just the climate conditions and besides whether or not the new neighbors are going to get along. There's things that we know for sure are going to affect these, affect where you find species, affect how those species are doing. Changes in habitat, well, we just heard some about how fire comes in and it makes it hard, under these new climate conditions, it can make it hard for the forest to regrow. I'll talk a little more about that in a second, but I think we heard a pretty good overview. Disease prevalence is likely to increase, at least for some diseases, might decrease for others. That makes a difference to the wildlife that are exposed to those diseases. Might make a difference to humans too. Some species might be able to move just fine and might not have a problem. Some species might be kind of stuck. I mean, if you think of a bird versus a slug, those two species have very different ability to move to a new place if they need to in order to get the appropriate climate conditions. Other species might be really good at adapting to new climate conditions. Either just they have really adaptable behavior, they can figure it out in their brains. Hopefully humans are in that category, but who knows? Other species, they might not have that ability to respond to different behaviors in their brains, and they might also not have a genetic capacity to evolve over time fast enough to keep up with climate change. And so if those species can't move, can't adapt, they might be out of luck. Changes in timing, I'll talk a little more about later. This is like the changes in the beginning of spring, the changes in when species do different things. Another thing is local variations in climate change. So, for example, precipitation. We don't know what's going to happen with precipitation in this area. We know it's going to get warmer. I mean, that's all of the models tell us that, and that's what we seem to be experiencing. But as far as precipitation, there's most models say it's going to get wetter in the north over the whole year, probably drier summers, but over the whole year, maybe a lot more rain or snow in winter. In Southern California, it's likely to be much drier year-round. A lot of the models say that. Here, we're kind of halfway in between, and we just really don't know. We know summers are probably going to be drier, but is winter going to be wetter? Is it going to be drier? Is it going to make a difference whether you're on one side of Mount Shasta or the other? Because it kind of sticks up there and might catch some of the rain. Changes in human land use can also interact with climate change to have effects on species, both positive and negative. And so in order to figure this stuff out, we need long-term studies. So, changes in habitat, just a little bit more. This is a picture of the Klamath Basin, right here. These are sub-watersheds in the Klamath Basin. And it's showing vegetation change. Don't worry about all these. I'll tell you what the important ones are. So, this green here is the evergreen forest, both of these greens. And this is a little bit in the future, 2035, 2045. This is farther in the future. These are 3 different climate models. And you can see that there's more broadly forest, that's what this gray and pink is, more deciduous forest coming in. On these maps, you don't actually see as much increase in shrubland, which is one thing that some models predict for some areas. But you see increases in grasslands in some of the models. And that's this over here shows the same thing. It shows a really big increase in mixed forest versus evergreen forest. And it shows some increases in woodland, so like an oak woodland. So we're going to probably be seeing some different types of habitat, but how those it makes a big difference how those things happen. If it happens like this, fire comes in and just the forest never grows back. That's like suddenly you're out a bunch of habitat. Whereas if you see a gradual shift where, different tree species are moving upslope, just like all of the animal species are probably doing, it's gradual, might not make as big of a difference. So, but more likely we're going to see things like this more of the time, and that's probably a problem. Another thing is forest pests, and we heard a little bit about beetles. Beetles, like any other animal, in general, we can expect them to go north, and we can expect them to go upslope, and that's really happened in Colorado and in British Columbia, places that used to be so cold in the winter that the beetle couldn't overwinter. Now it's warmer, the beetle can live there, and it's really, it's really done a number on some of the forests. Huge swaths of forest have been kind of wiped out by the beetle. Here it's native, so we've had it, but drought conditions, more fires, it could become more prevalent. There are some other diseases, they're fungal diseases rather than insects, but they could become more prevalent in forests if we get wetter conditions. So if it's drought, we have one pest. If it's wetter, we have another pest. I don't know. It doesn't look too good. For the forest, now, a species that likes to live in a shrubland might be happy about this. And so speaking of diseases, but switching to diseases that attack animals rather than trees, West Nile virus is one that's been pretty well publicized. It's an introduced disease that it's not native to North America, but it seems to have established here pretty well. And this map shows in red areas that are expected to have an increase in the probability of West Nile virus by 2050. So you can see, actually there are some areas in Northern California that might see a decrease, but they're pretty little compared to all the areas that are going to see an increase. And so this disease is spread by mosquitoes, and it attacks all kinds of birds, but there's a study on crows showing that it especially reduces the population of crows in areas that have a lot of human development, probably because the mosquitoes have great breeding habitat in people's backyards. So the study was on crows, but it affects all kinds of birds, and if it's really abundant in the bird population in an area, you can kind of expect that it's going to be affecting people as well. So this is, a lot of this wildlife stuff is not just, think about all the cute wildlife and we feel sorry for it. It has consequences for humans as well. So you might be wondering why I keep talking about birds. And the reason is that there are a lot of studies on birds. There's a lot of data. A lot of people I don't know if we have a lot of birders in the audience, but a lot of people who just like birds go out and look at birds. They write down what they see. And there actually, for a very long time, have been ways to send those lists of birds and when you saw them and where you saw them into people who are doing studies. So this is actually from 1938. The USGS has this stash of these old data cards. They go back past 1938. And they're entering them in, and they can use these data for studies. eBird is one is a website that's popular now. You can go there and you can enter your bird data, and those data that get entered into that site, they get used in these studies. I don't know if you can see this. There was actually, I have a report that came out yesterday at school. You might have heard about it on the news. The Audubon Society just released this report about 314 species that they say are threatened due to climate change. They're using the word threatened in a different way than the way I used to begin to talk. But a lot of species are losing parts of their range due to climate change. And so they did this big study showing you all these maps of that. And you can find that online. I'll have the URL at the end of the talk. So anyway, there's lots of data, both from citizen scientists and from professional scientists who just go out and do these long-term studies. Another thing is that there are a lot of ways for climate change to affect affect birds. So a lot of birds winter in south and breed in the north, and they fly up all these lines during spring, and they fly down again during the fall. So there are a lot of different places and different times of the year when they can experience climate change in different ways. We heard about how it's warming faster in the north than it is in the south. So you can imagine if you're spending your winter down here and you're not seeing much of a difference from one year to the next. You might leave at the same time at the end of the winter, and when you get up here, you discover that it's summer already. You missed spring. So that can be an issue. And that issue is called, this is a very big word that confuses people, it's called the phenological mismatch. So phenological just means anything having to do with the timing of an event in the life of a living thing. So, when does a deciduous tree leaf out? When does a plant flower? When do caterpillars hatch? When do animals mate? When do they hibernate? Any of those things, that's called a phenological shift, when those things change in timing. So climate change is leading to earlier spring events, and a lot of those things are shifting earlier. Things like hibernation that happen in the fall might shift later, and then waking up from hibernation might shift earlier. Birds don't hibernate, I don't want to imply that. But so one thing that's happened with birds, and this has been shown pretty conclusively, and I think first for a species called the great tit that lives in Europe. They come in, and maybe they're getting to their breeding ground at the same time, so they lay their eggs at the same time as they did before. Now before, this is what happened. The caterpillars hatched and got more and more abundant and bigger and juicier. And right at the time when the chicks were in the nest, saying, feed me, there were caterpillars all over the place. There's plenty for them to eat. Well, now what happens is, spring is shifting earlier. The birds don't really know about it. They were down somewhere in the south and didn't get the message. The caterpillars are hatching and becoming abundant earlier, and by the time the baby birds are ready to eat the caterpillars, there's not so many caterpillars around. Although there's recent data showing that these birds have been able to adapt somewhat and eat different food sources so that their populations aren't decreasing. Not every bird is necessarily going to be in that situation. And there's a picture of a hummingbird here because hummingbirds take nectar from flowers. So they have the same situation if the flowers bloom earlier and provide their nectar earlier, but the hummingbirds wintering in the south didn't get the message and don't get there in time. Even without migrating, there can be problems. So this is the gray jay, and you probably are familiar with this species that lives around here. It's sometimes called the camp robber. So they like to sit at picnic tables and beg for your crumbs. And if you give them your crumbs, what they will do with it is they will stash it. They'll make a little bolus with their saliva and they'll stick it someplace. And they do that with all kinds of different foods that they scavenge. A lot of birds stash seeds, but they'll stash pieces of meat that they got off a carcass. That's perishable, right? If you were doing that at home, you would put it in the refrigerator. And they rely on the natural refrigeration effects of snow and on winter time to keep their food fresh over the winter while they stay in place. So the birds that you see, if you go up high in elevation where they are, the birds that you see there are going to stay there over the winter, and they're going to lay their eggs and make their nests pretty early. And they're relying on this stashed food that they have to stay cold and get them through the winter. And the autumn is coming later, and their food is spoiling. And that's leading to them having lower populations. This is a study from Crater Lake. So we're near the south end of the range. Crater Lake is also near the south end of the range. And chances are, at some point in the future, we're not going to have these birds around anymore. They'll be in Ontario, but they won't be here. So that was a lot about birds. Now we're going to talk a little bit about the this Grinnell Resurvey project. This is some work that's coming out of UC Berkeley. And it's possible because this guy, Joseph Grinnell, he was the director of the Museum of Vertebrate Zoology there, starting in 1907, which was the beginning of the museum. He had this great idea. He led all of these surveys. I'll show you the map across the state. And he had this thought, which was, I'm going to go figure out what's out there now. I'm going to take specimens and I'm going to write everything down. And 100 years in the future, the researchers who are around then can look at this stuff and they can compare the changes. He probably didn't know about climate change at that point, but he was thinking things might change and this will be a really good resource for people in the future to know how they changed. And he was absolutely right. So they took these expeditions, they wrote everything down that they saw, and they collected everything. Here's an example. They took pictures. It's Yosemite. They did a lot of work in Yosemite. Here are all the places they worked. So I'm going to end up talking a lot about the Alaskan transect because it's pretty close to here. But this is where they did a lot of work that they've published so far has been from the Yosemite transect. And I haven't seen anything published yet from this transect, and I'm not close enough buddies with them to know what their secret data say. Hopefully they'll publish something soon from that, so we'll know. So again, please don't try and look at everything on this slide, but if you can see here, if you can look at this one, this is from Lassen, and the blue on here represents changes in precipitation between the first survey, which was like in the 1920s, and the latest survey, which was a few years ago. So this is going up in elevation as you go from, let's see, from your left to your right. And you can see that there have been increases in precipitation throughout, all the way up in elevation over this time period, and really large increases in precipitation at the high elevation sites. You can't really see what's happening with the temperature because relative to the changes in precipitation, it's really small. But I don't know if you can see it, actually the arrows are pointing up at low elevation. I think they're pointing up. I have a hard time seeing it. They're actually pointing down. So, in spite of the overall trend globally for high elevation sites to get warmer quicker, on this Lassen transect here, it's actually getting cooler at the high elevation sites. What's going on there? Maybe it has something to do with this precipitation. But so if you think about where those animals would have to move in order to keep their climate the same in terms of precipitation and temperature, the ones at low elevation would have to move up either way. The ones at middle elevation might, they might be kind of torn. Do I move up? Do I move down? I don't know. Because temperature might be telling them to move up and precipitation might be telling them to move down. And the ones at the highest elevation would move down, actually. And so, what did they see? Well, they saw species going in different directions. So this just shows, whether the temperature and precipitation directions that they would have to move to match. And here was what, down here at the bottom, is what they actually saw. Each of these bars is a single species that they saw both in the earlier study in the 1920s and in the recent study a few years ago. And the green parts of the bars show that the species moved into those areas. The red parts of the bars show the species moved out of those areas. And as you might expect, the bottom is the low elevation and the top is the high elevation. So a lot of species at low elevations moved up at the top end. Some of the species at the high elevation moved up at the bottom end. But there were some species moving down at the top end of their elevation range. Overall, the only thing they saw that was didn't look like noise on the Lassen transect specifically was that species shifted their lower elevation limits upslope. So overall, the only thing was that they were shifting upslope, but just at the low end, not at the top end. So it sounds a little like they might be contracting, but they didn't necessarily find that. Overall, they were finding that species were moving around, and this was on all of these three transects. Species were moving around. They were tracking either the temperature or the precipitation, but it wasn't necessarily predictable which one. Another thing that they found is that golden mantle, ground squirrels, and buildings ground squirrels, which live at high elevation, are getting bigger over that time period. This is because they hibernate for a shorter period of time and they can spend more time eating. You eat more, you get bigger. There have been similar results in the Rockies for yellow-bellied marmots, and these ones are actually, the populations are exploding because of it. But for the lower elevation California ground squirrel that doesn't hibernate, they stay the same size, they didn't change. In general, this does not necessarily mean that climate change is a benefit to high elevation ground squirrels, because they're losing, this map shows that they're losing the low end of their elevation range, and they're not gaining at the high end. The green, you probably can't see these symbols well enough. There are green symbols on here that show places where they were before and they still are. The black symbols show places where they were before and are not now. And on this map, the high elevation is kind of in the middle of the map. So there were some lower elevation sites where they were able to hang on, and those sites were places where people had campgrounds or agricultural fields. They were able to hang on to those places, but at the same elevation, if there wasn't a campground or an agricultural field, they were out of there. And that's because there was shrub encroachment on the meadows that they liked. So in this case, human use of the landscape is actually helping these animals. It's giving them a food subsidy. But that's not always going to be the case. So, is my cat out of batteries? No, there it is. So this map, what it shows is there's a change in the probability of species being there, like all those maps I showed you earlier. But it also shows the change in housing density that's predicted to happen in the future. And these are for a number of different birds that breed in California. And so all the blue parts of this map show places where a lot of species are predicted to move there, but there are also a lot of housing developments that are predicted to happen there. And if a housing development happens, what does that do to the bird's habitat? It might be good for some birds that really like backyard bird feeders. It might be terrible for other birds that like to, nest in hollow trees. That there probably won't be as many hollow trees if you have people's houses there. So, you have to think about what's the human factor going to do when you think about the species moving around the landscape. So what can we do to conserve wildlife through these changes? There are all these different lists of R words, but in general, the idea is you want to try and figure out, you want to try and build in redundancy to your conservation network. So you want to have more than one corridor that animals can move through, because if that corridor gets cut off because there's a fire and the trees don't grow back, well, that's it. Species that need to move north might not be able to. And another thing is resilience, which I think we're going to hear about in a minute. Trying to figure out, how to manage. If you're managing your landscape, can you build in some way to make it more resilient to these changes, so that it won't just fall over at the first sign of climate warming. So there are all these different organizations, federal, state, private, that are making these plans for how to do these things. And in case you're interested either in reading about climate change adaptation or putting your, the list of birds that you see in your backyard as eBird, or looking at other people's historical bird data, or just looking at what science says, here are some things. And I don't know if we have time to just leave this page up, but
We can leave it up while we have a couple questions before we move on to the next. 2 or 3 questions?
We have our emails. Is it possible to email that to us?
I have the emails.
yeah, I can certainly.
That'd be great. Thank you.
On the list of R's, I saw representation. And what did you mean by that?
Well, okay, I didn't make up those R lists. I've heard people say, oh, the 3 R's, oh, the 4. People like to give these lists of R's. It's kind of like reduce, reuse, recycle, right? Somebody came up with that, and now everybody needs R's. Actually, it's older than that, isn't it? Reading, writing, and arithmetic. But what it meant in that case was making sure that the species that you're trying to keep around are represented in your conservation networks currently, because if they're not there currently, they're not going to be there in the future.
And by redundancy, for conservation, were you speaking to just a series of elevations or habitat types that are likely? Or
No. So redundancy, in that use of the word redundancy, there's a couple of different meanings. One is to have different populations of the same species, so that if one gets wiped out, you can still have another one there. Another one is to have different connections between different patches of habitat.
So both landscape and species population?
Yeah.
Or habitat. Thanks. Right back here.
In the purple shirt.
Yes, I see a lot of government networks here, and the government does not seem to be funding anything to help this wildlife. They are against it in every way, from logging to doing all the chemtrails and doing all the pollution of water and the harvesting of drugs, and all of this is, the government is not doing nothing to help.
Well, so I work for the government. It's not just one monolithic organization. Parts of it are trying to help, parts of it probably aren't. So these particular government agencies that are involved here are mostly the research-based ones, or the ones that really are trying to do something for wildlife. And of course, we always think we're underfunded. So, you know, if you want to write to your representative and say, do more to help these things, please do. But that's just my personal opinion, by the way. I'm not speaking for my agency, but I like being able to be paid to work on these things. There are a lot of people in the government. Like I said, it's a heterogeneous organization, and I think some of them definitely would feel sad, like me, to hear you say that.
Thank you. You're doing a good job to bring it to our attention.
So we're actually going to move on to the next speaker now, and if you have more questions, Catherine, please keep them in mind and ask them again at the end. So I'd like to introduce. So for our final speaker, I'd like to come and introduce Todd Hamilton. He's a forester with the Shasta Lake Ranger District with the Shasta Trinity National Forest. He's been there since 2010, working on forest health and public safety within the National Recreational Area and hazard tree abatement after wildfire. He's currently a silviculturist for the Highway 89 project on the Mount Shasta McLeod Management Unit and is in the final steps of national certification. Starting in 2003, Mr. Hamilton worked with the Redding Silvicultural Lab at the Pacific Southwest Research Station, specializing in east side forest systems and the effects of vegetation management on fire behavior, fire severity, ecosystem dynamics, and forest recovery. He received his master's in science from Humboldt State University with an emphasis in conservation and environmental ethics. So, Todd.
Thank you, Kara, and thanks for picking such a subject matter, climate change. Not an easy one to cover by any means. As you heard, models are kind of different from one another. So it makes it hard to interpret at times. But in a nutshell, I do want to cover a few fundamentals. And so consensus for any non-believers, there's some folks in the scientific community that actually do believe there's a climate change effect. Historic conditions might show that with ice cores, as far as carbon concentrations, specifically atmospheric. Is there a relationship between carbon and temperature? We'll see. And then, of course, as Carl kind of filled in and such, is there's disturbance regimes. Disturbance, all I mean by that is something that shifts what was going on before, something that interfered with the current growth pattern. Future predictions. It's getting warmer. Summers are getting longer. It's getting drier. And there's some effects. So all the models are wrong. I'll tell you that now, but they're useful. Believe me on that or not, that's entirely up to you. But more importantly, what are we trying to do about it? how are we going to use these models to kind of adapt and perhaps even mitigate current problems that we might have. So essentially, I'll show you a bunch of fancy graphs and photographs, and hopefully you guys will be able to carry along from that. So IPCC, Intergovernmental Panel of Climate Change. There's no doubt, basically. That's what they're saying. People are probably the cause, and we're probably the ones responsible to help make it better. NASA folks, this decade for the most part, it's the hottest on record. The following year, in 2011, the tied the hottest record. National Research Council, or the Academy of Sciences, if you do the same little thing we have been doing, good luck with that. And then PNW folks representing kind of Oregon and North are saying that the most significant short-term effect is going to be the shift in the disturbance regime. And I tend to believe because, I mean, they have logos. I don't have a logo. It's good enough for me. But this is kind of what it boils down to. Carl went back 1,000 years or something. We can go back further, and it's going to tell us something different. Well, let's go back a long ways. And we know it's cyclical. Things go up and down. That's just life, I suppose. But what's different is this is where it's topped out. And this is where we are today. We're practically off the chart. That's just carbon. My interesting thing is, let me back up. Take this and smash it down a little bit. This is the same chart. So what you saw in the last one is the red. And now what I'm showing you is temperature in blue. Now which one came first? I don't know. But there's a relationship. They're kind of going with one another. So if carbon is having an effect on temperature, I kind of tend to believe it. Cause, that's not a hard one. Some people don't think it's human caused. Okay, that's fine. Here's the top 10 developing countries. I took this out in National Geographic if you guys are subscribers. If you look at all the carbon that we're using, the energy that we're using, it's kind of distributed. We have natural gas, some oil, and a whole lot of coal. And what you're seeing on the right graph is coal. So this is Australia, for example. On the left-hand side, that's 2000. Right-hand side, that's 2011. So it kind of shows you, are they changing the last decade? Have they increased or decreased their use of energy? I don't blame China for growing, for developing. Heck, all of our fancy old 50s vehicles are in Cuba. We all develop at different paces. But that's just kind of interesting. It's happening, and there's no doubt about it. And we can slick off mountaintops in West Virginia and export it to China, but there's an effect of doing that. So these models are wrong. But they're showing something that's consistent. So this is one model, let's say Australia, and then this model is the Japanese model. One's perhaps more sensitive than another, but they're kind of showing the same thing. So if this is seasonal temperature, and I'm using what I think is hot, June, July, August, on both of these graphs. And if we're sitting right up in here, you're still looking at 2 to 3 degree increase. And that's the robust model, the one that's real sensitive. You're sitting up here, 3 to 4 degrees. They're saying something different, so they have to be wrong, but they're both going up. That's a trend. That's something I believe. So we're looking at precipitation. Maybe it's going up, maybe it's going down. Depends, I think, on a lot of microclimate and big scale stuff. But likewise here, Australian model on the left, Japanese model on the right. This is less sensitive, that's more. So if I'm now looking at winter, December, January, February, we're looking at possible a little bit less precipitation here. But that's different than what you had. Possibly precipitation is going up. So we're both wrong. And then it gets kind of fuzzy in here, but in either case, it's definitely showing something changing. So don't forget, we're looking at data from 1960 to 1990, and then taking that information and trying to project it out to year 3000. That's what we're expecting to have. Or 2100, sorry. That's a big difference, isn't it? Way different. But there's kind of a trend that is fairly consistent that we should all be noticing. Vegetation or veg habitat for critters, at least in the northern hemisphere, they're going up in latitude and they're going up in elevation. That has some implications. Just climate change in general. And we know most of this stuff, you guys. I mean, droughts and floods, dust storms, heat wave, hurricanes, come on, Katrina, Sandy, ice melts. Next thing you know, you have the ocean in the New York subway. It's happening. It's happening now. Which can lead to stuff we talked about, people maybe don't think about is war over natural resources. Which is why I like Mark Twain's quote. There's a lot of truth in that one. In an arid climate, water is way more important than anything else. Oh, and I don't think that's real. Do you guys? I think that's photoshopped. I didn't do it.
That happens.
It probably, yeah. I have an actual photo of two of them like that last, but minus the lady. But what I can really deal with as far as a manager, I can't really deal with hurricanes. I can't deal with oceans per se, which is probably the majority of our kind of influence on climate change. But I'll look at insects, disease, deforestation, and wildfires. That's something I can kind of grasp. I can manage that, perhaps. Social dynamics, I'm horrible at it, so forget that one. So, turn of the century, 1909, we have a photograph on the left-hand side. Maybe it's because it was pretty in Park Lake that they took the photo, I don't know. But in 1948, 40-ish years later, a little bit more growth. And you can't read that it's 1989, a whole lot more growth. I think that's just happening in that one spot? Everywhere. So is it just fire suppression? Probably not. You know, we slicked off a lot of woods, we brought in some grazing, changed the fire regime ourselves by suppression. But I'm guessing that fire went in here probably had limited effect. It's going to be on the surface, maybe a couple foot flame lengths. When you get to the far right, that's going to explode. And you won't have any big trees left. That's what I'm dealing with. I mean, that's the thing we're all dealing with. The fuels are growing, and we're not doing much about it. At least not the rate we should be, perhaps. So, what's going to happen? Wildfires are going to increase. We got 100,000+ acre one burning right now in Happy Camp, Beaver Fire. Heck, I had one just start when I left this afternoon. Started in Bella Vista. Rim Fire last year, Bagley Fire, and so on and so forth. All this stuff, if you remove cover, it removes the interception of rain. What happens with that? You get more surface runoff. What happens with that? It goes somewhere. Probably our watersheds. So an example I have here is from a recent Bagley fire, which is not too far from here. So on average, if you're on a wreck, we're putting a little project together, raise the dam, just a small one. You have, on average, about 240,000 tons go in there on an average year from normal cover in the absence of fire. So what is 240,000? Think of your pickup. It's about 240,000 of those go in. After the fire, however, 1.7 million tons. That seems like a big deal to me. So not just wildfires are going to get bigger, but it's going to increase the amount of erosion. I don't want to be Armageddon, but it's just kind of trends. Insect and disease infestations will often expand, perhaps as large as or even larger than some of the effects we're seeing from wildfire. Mountain pine beetle is a big one. That's more kind of inland. We're dealing with more of a western pine beetle, but also the root diseases that go with it kind of interact with one another and make a whole other problem. Again, I'll keep saying this, it's going up. That affects the birds, it affects the charismatic megafauna as well. So what I do with habitat, what I do with vegetation is going to affect other things as well. So annual area burn in the western U.S. Carl might find this familiar graph. But starting in 1970, we'll just take that out to roughly today. This is the area burn. And all it really matters is it's getting larger. So if you're imagining to put on a slope, it's going up. At least the red lines. Blue line is what logging we used to do, how much wood we used to pull off of our public lands. See a trend there? As that goes down, that goes up. It's anecdotal, I don't know.
That's,
Interesting, nonetheless.
that's correlation, not causation.
Then you can add, so if timber slope is down, wildfire is up, and the risk of forest loss from insects and disease is getting riskier. This is the new map that we have, that we get to work with. So if you put insects, bugs, and crud together, and you predict what kind of loss you might have in acres of forest cover, they're predicting 71 million acres gone. Now that's the entire U.S., okay? But if you look at the other half, which I didn't do, there's really not much out there. So we're looking at 90% of it's going to be out in the west. So when you're working with people in the east, they say they make all the money on bird's eye maple, sugar maple, and cherry, and then they ship all that money out to us to fight fires. There's kind of a lot of truth to that. So fire's going up, logging went down, insects are going up. That's what the red is, by the way, if you didn't notice. I couldn't tell. So, you know, I'm part of an organization and I'm at the bottom of the pile and I get told what to do a lot, and so this is just one of those things. What's the leadership's intent? They recognize this stuff. They're not, I mean, come on, they're not oblivious to these changes. So it's saying water's the most important, but there's some major roadblocks we're going to have. Decreasing precipitation, overstocked forests, which you saw in that one image, and human population growth. China's grown, India's grown, we're grown. Wildland-urban interface is growing. So what do? As far as ecological restoration, you've got to increase the pace and scale. This 100 acres here, 5,000 acres there, it's pittance compared to the landscape. It's not doing much. We've got to go bigger. So they're saying, it's an arbitrary number, 500,000, whatever, sounds good to me. But you've got to focus on some areas. Meadow restoration, road maintenance, people don't think about that. How are you going to fix a road if you don't have money? Mechanical vegetation treatment. They didn't say hand felling, they said mechanical. Fire management for resource benefit, not fire suppression. Very specific words. Most importantly, I think, is working with your neighbors. I don't think we can do all this on our own. And if I can tie that stuff in with my neighbor and make one continuous break, or one continuous treatment, we might have a better chance. If in fact fire is your biggest fear. So anyways, it's much more fuzzy stuff. I don't know what the hell they're saying half the time anyways. I gotta put it in a context that I do get. Mitigate for stuff we're dealing with now, and adapt for those trends that we kind of think we know for the future. And silviculture is gonna come out, I can't help it. So there's a bunch of stuff here I can clarify later if you care. Collaboration, you know about variable density thing, whatever, we're just saying, stocking control. Advanced regeneration, utilize trees that are already there instead of having to plant. Artificial regeneration, actually planting them yourselves. Maybe that is of the best interest because you can select the spacing, the species. Maybe even use rust-resistant stuff that you've done a little genetics on. And tree improvement, not GMO, difference, big difference. These aren't tortoise cells going into a tree. This is Shaquille O'Neal, with Shaquille O'Neal making a bigger tree. Increase your species composition. If you have all one thing, and you do have a disturbance or an insect or disease, it's likely to wipe it all out, so mix it up. Promote fire-resistant vegetation. We'll get into that a little bit more, but if you have something that's not resistant to a fire in a climate that loves fire, you might have an issue. Age classes, all I mean by that is I want big trees, middle trees, and little trees. Process restoration, I'm kind of making this up as I go along, but it makes sense to me. We need to restore fire back to the landscape. And then is it actually working? And if it isn't, try and adjust. That's what makes sense to me. I can take the warm fuzzy and put it into a context that I can work with. That's what I'm doing.
I have a question about this. I've thought about it, but you might actually have data on it. We do need to, burn off all this extra ground cover that we've been suppressing. But at the same time, that's going to add to global warming, which is going to further the problem that we, apparently most of us here agree on. So how much would that increase global warming? I mean, it's a catch-22 to me.
Yeah, but pay me now or pay me later.
Do you agree? I mean, that it's a catch-22?
It is, but we'll get into that.
Okay.
Yeah. That's a good question. Yes?
And logging companies, I just does here, we have a large timber company, and I noticed on Google Earth, my cousins were showing me, and it didn't look bad to me. They have on the other side of our ridge, which we can't see, all the 10-acre or 20-acre cuts they've been doing, and to me it looked like, well, maybe that's good because they're thinning and we won't have such a huge wildfire. Do you think that that's an answer to do more selective, well, they are clear cuts?
So yeah, that's good. There's thinning and clear cuts and not the same.
Well, I
The
know
state
that-
has different regulations than the agency does.
But it's thinning a large piece of forest by making small cuts in it.
So if you think about making small cuts, that breaks up a continuity. So if I'm burning across vegetation that's all the same, then I put a line in it, which is what fire folks do. But you break up what is there. So if you have patches here and there, you're likely to break up the spread, the continuous spread. Therefore, you have a better chance of perhaps suppressing it, diverting it, flanking it, whatever. We'll get into that as well.
Is that effective, you think?
Yes,
So,
it is.
thank you.
Yep. So migrating line project is fairly large, so they told us to pick up pace and scale. Oh God, we did. You can't really tell. I don't know if it's out of focus, but that's a section right here. That's a section. So if you know, each section is a mile wide. It's like 15 miles wide. This is east of McLeod. So if you guys know, that's the McLeod River in here. So cattle camp, Camp 4. Lower Falls. I don't know if you guys are familiar with that area. And this is kind of towards more Mount Shasta. So this is I-5. That would be 89 intersection there. Snowmans. Collectively, we're looking about just shy of 14,000 acres. A little bit more than the 5,000 we might have done in the past. And within that, we have a whole bunch of stuff going on. You kind of have to simplify it, break it down into something I can wrap my brain around, and I have. And so I have FUs, fuels units. We have plantations.
You might want to work on that acronym.
Yeah. We have two, so there's FU2s.
You might want to work on that one too.
I might get in trouble for that one, yeah. That's why I'm not wearing a uniform right now. But plantations, I'm calling those early seral. We also have stuff that's not plantation. But they're kind of mid-seral. It's not old growth, that's gone. It's been slicked off the turn of the century. But I have 4 footers in diameter that are only 65 years old. It's amazing. Anyways, we're trying to do some stuff. We have things on the highway, big trees that could collapse and maybe it hits somewhere. That's not okay. We already have trees, when they get snow, they slough and it's breaking windshields. It's so thick in some areas that deer pops up and you don't have any reaction time. So restore that as well as infrastructure, buildings and such as well. But we also want to restore some other stuff, oaks and aspen. People may not realize there's probably a whole lot more oaks in this country than we kind of recognize today. Aspen are a keystone species. Their presence alone can indicate a healthier system. And without them, you wouldn't have other interactions with other critters. Restore wet and dry meadows, bitterbrush, for example. Fairly important browse species. Really nutritional, but when they get old and decadent, they lose that nutrition. Riparian hardwoods. I have alder that are just screaming for sunlight underneath some of these conifers that are approaching. Structure and process. We'll go over that a little bit. Ecosystem health. That's just kind of everything together. But what's amazing is a lot of this was big wood. We slicked it off. It turned to brush. Fire ripped through. Then we did these brush to trees stuff. We went road, planted trees. Well, now we have a bunch of plantations, which again is this light color, so it's everywhere. So now there's a pivotal step. What's the new trajectory? We got it back to a forest from brush. That's a good thing. Do we want to keep it in a plantation? I won't answer that now. So I've taken some plots. We've taken a lot of plots to figure out what the heck we have out there, because I need to know what there is to figure out the difference so I can know how to get there. So in a nutshell, what I've done is chicken scratched on a cocktail napkin, trees per acre, this axis, and diameter at breast height. So this is a box plot showing a more abundant population of 6-inch diameter trees. It's called a reverse J. So as you go out to the larger trees, there's just fewer of them. That's what we have right now. A lot of little trees, not so many big trees. So if I could, it was that simple. I just smash this down and shove some of that over and get a better distribution of both small, medium, and large sized trees. And we can do that. It just takes time. Likewise, what we're seeing is, let's say it's pine dominated in overstory, that's fire tolerant, shade intolerant. And we're getting a bunch of fir and cedar in another story. What I like to do is maybe pluck the tree out here and now, release those guys as well as release those. And get rid of some of those, the abundance of those smaller trees. Ideally anyways. Oh, by the way, that stuff up top, that's how much we have currently, as far as species composition. Whole lot of ponderosa pine, not much black oak, and a pretty good amount dug for incense cedar. There's even some aspen sneaking out there. I didn't put it up.
So those are percentages? By stem count?
Yeah, trees per acre by that diameter class. Yeah. Or excuse me, just trees per acre by that species. Yeah. So you could have, this many, that would be a certain percentage of that, and it's not base layer.
Yeah.
So hey, this is pretty, this is gorgeous, right? You got this beautiful grassland underneath, big large pine in the overstory. But it's pure pine. It's about 200 square feet, if you guys know what that is. It's kind of high for pine. And I'd say it's resistant to fire. So if I got fire in here, that's not going to crown out. It's going to be fine. But is it resilient? And is there a difference between resistant and resilient? Resistant, you can ward off that disturbance and still be there after it's burned over you or eaten through or whatever. Resilient means you need to maintain that function over time. So what I would argue is that because it's all the same age, same spacing, same species, same diameter, it doesn't have much longer before insects, disease start to take over. So it looks pretty, it looks great, but for how long? There's one of my favorites. I got a comment in one of our documents that said there's absolutely no scientific evidence that thinning stands increases growth rates of residual trees. Meaning, if I go in a thin stand, the trees that are left there, they don't respond. Well, that's a crock. Right? 85 years, and this thing only grew about 5 inches. 85-year-old tree, that big. We thin it in 9 years, it doubles in size. Every tree is about 50% carbon. So if you increase growth rates, you're increasing sequestration. We used to call that volume, but now the buzzword is sequestration, so I'll roll with it. That's sequestering, storing a whole lot more carbon at a faster rate than it was before it was thinned. And people ask, well, what happens when you remove that wood? Is it not just being part of the release in the carbon cycle? Well, what if we create jobs, store it long term, and put it into furniture? That doesn't seem to be releasing carbon very fast, and why can't we do that? So we store the wood by turning it into a wood product, as well as release the stands that are out there. And when you do that, guess what happens? You change the fire severity, the fire intensity, the fire behavior. So when it does burn through, you still have forest when it's said and done. So, what do we do in plantations? There's a lot of them out there. We've converted from brush back to trees, but now they're all the same age, same size, same species, and so on. Well, my goal is always to grow big trees fast. but it's even age. Let's make it more than one age. And we can do that by what's called group selections or patch cuts or selective openings. Just plop holes. That allows another generation to grow in that white space, that new space. We can increase species diversity. We talked about advanced regeneration, artificial regeneration. Here's an opportunity perhaps to adapt. So if I have trees that are existing currently at 2,000 feet, I want to plant that. But I know climate change. I know that things are going to move up in elevation, move up in latitude. What if I took species, seed stock from 1,000 feet, because I know it's going to go up here, and I assist that migration and plant it at 2,000? That's what I plan to do. I'm going to assist that migration and adapt to the possibility that this climate change is real. This is the growth rings that you saw. You can increase, if you see big rings, probably pretty healthy. And then prescribed fire. You can't just cut. To me, that's just changing the structure. You haven't restored the process. Fire is a major process. And, there's down large wood, the wildlife people need to have, so we'll just leave it out there for them. So now we have plantations. It's a slightly different animal. It's not even age anymore, but we do now have some opportunities to really enhance some beautiful characteristics that exist on that landscape. Of course, you grow big trees fast, that's always going to be there. But we have things that we can do like radially thin. I found a big old black oak, 24 inches, and it's just inundated with dug fir. I can maybe clear out that dug fir and release that black oak, produce more mass for wildlife. Maybe I want a picnic underneath that later. Aspen, legacy trees, all I mean by that is the big ones that didn't get slipped off. They were little geeks back in the day, they got released and now they're monsters. Then fire tolerant species. When we do that, we always think about some can tolerate higher densities than others. Fir can handle way higher density than pine. So I'm always thinking about that as well. I'm also looking at diameter distribution. If you have, this is what's going on right now, I guarantee it. We're thinning from below, putting upper diameter limits in some areas. What happens in time? They all grow up and they all kind of die and there's nobody to replace them. Well, I want trees of different sizes, so as one maybe gets cut or one dies, I have another generation coming up to replace them. There's fire again, then the downwood stuff again. So kind of just to wrap it up here, whether you believe it or not, it doesn't matter, but if I'm placing bets, I'm going to bet that it's happening. Because if I'm wrong and it doesn't happen, so what? Right? But if I'm wrong and it is happening, then that's not too good for my grandchildren. And of course, Forest Service, or not a single agency is going to be able to solve this problem. I mean, it's bigger than any one of us, any agency at all. But currently, this chasing fire thing, it ain't working. Right? You can drug, so this is what it comes down to. We can react. We can react to an event. It's going to cost you, let's say, $5,000 per acre. That's about what it is right now. Or you let me be proactive, talking about doing all the stuff I just discussed, thinning, radial release, artificial regeneration, plantings, off-site. It's going to cost about $500 an acre. Oh, and by the way, when a fire rips through there, you still have a forest. Versus reacting like we're doing right now. So this is what I'm trying to do, to keep it simple. Go in there, do mechanical thinning first. Get it prepared for that disturbance. And I say mechanical because of the scale that we have to do this. We can't all go out there by hand and achieve this objective over such a large landscape. And then to restore the process. Restore the structure, that's one thing. Restore the process, I think you're starting to complete that loop. But it's going to be smoky. So for infants, elders, those with respiratory issues, that might be a problem. Maybe now, maybe later. That's kind of the picture that I'm going for. This is a research natural area in Alaska. It's been burned a few times, never been cut. That's kind of what we're shooting for. You can burn in there, you're releasing some smoke, but compare that to a huge wildfire. 2008, for example, released enough emissions that if you ran 1.7 million vehicles simultaneously, that's how much emissions was released in that year alone. Pay me now or pay me later. A little bit of smoke under a controlled environment. Controlled is a loose term, I guess. I think that's an illusion, right? But in a semi-controlled environment, sure, we're going to have smoke, but it's kind of greater good. Break some eggs to make cake. That's kind of it.
Just don't do it on a windy day.
All right, we've got 15 minutes for questions.
I have a couple questions about that 500,000 acre regional objective. Did I get that right?
Yeah.
Okay. Does an objective of that size keep up with growth? That's the first question. And second, is an objective of that size supported by the budget that you get from Congress?
Absolutely not. This is what drives me nuts. It's warm, fuzzy, blah, blah. And it's like, I'm trying to apply this on the ground. Show me the money. So we'll give me a regional direction, and I'll try and apply it. But we are. I mean, we're definitely going for it. We definitely have hiccups, and I'm not going to give up. I'm still young and ambitious and full of it. But you're right.
When was that objective issued?
January of 2014.
Oh, so you're in the first year, okay.
You got it.
How close do you come in this year?
I haven't looked at those. I'm not a bean counter at the regional level. I don't know.
Okay.
I really don't. Yes.
So did I take that budget question? The answer is no?
So right now, 75% of the Forest Service budget is going to fire and fuels. 25% is for the rest of us who are trying to manage the stand to be proactive. I think the cart's a little bit backwards and front of the horse.
You know, driving, I guess, east and south out on 89 towards Quincy, there's a long run to there with a lot of really extensive things. Is that stuff that you guys have done?
There are some plantation things that are fairly recent that are from us.
And big trees left, lots of the middle-sized trees gone,
Yes.
and chipped and ground up.
Those are a lot of part of the alchemist cells that are fairly recent, and yes, some of that is, but I don't know exactly what section you're talking about. There's a lot of private in there as
Well,
well.
not towards Medicine Lake also within really thin there. But, so is that part of this process of getting the forest back to the right density?
Yeah, exactly.
In the past, it seems like the Chesapeake has been reluctant to allow managed fires like in the wilderness, et cetera. Is that going to change in the forest plan? I know
Yeah.
you're a proponent, obviously.
Arlen had this thing, there's two kinds of fires, wildfires and prescribed fires. And you put out wildfires. That's changing. We're talking about managing wildfires now. What that means, there's a lot of liability associated with that. And a lot of us younger guys coming into a system that we don't have the experience that, Carl's been doing this stuff. He's been on the district for 30, 40 years. So we're trying to figure out as well.
Me?
Yeah.
Yeah, I've been, just to give you a little context, my original major in college was climatology, along with, Al Gore. I took the course. So I've been looking at global warming for, 35 years or so. And, then in grad school, I was studying environmental education. That's what I studied. And I called the head of the state one time and asked her about their program that they had just implemented. This was in Arizona for environmental education. Well, it was about teaching about the squirrels and the flowers and all that. And I said, well, what about the big picture, global warming? And that was it. The conversation was over.
Yeah, you're cuckoo, right? What do you think? Global climate change.
That was 20 years ago or something. But the point being that you guys are saddled with presenting it from your fragmented perspective, excuse me, but our society fragments everything. Sure. And so you touched on very briefly on, I think at one point, on the idea that we need to use less resources. Well, that's an individual thing, and what I came to realize after 40 years of frustration over talking to people about global warming and getting nowhere, including in this town, was that I needed to just set an example by using less energy myself and certainly not having any more kids and things like that, because that uses energy. And Americans need to connect that. I mean, I know I'm lecturing here, I'm on my soapbox, but the point is this, is that we all now need to step up and accept the responsibility, not just what you're talking about, which I agree with a lot of, and I don't have enough knowledge to know if I disagree with other stuff, but we all need to step up and start using less energy, especially things that cause global
In
warming.
the interest of time, is just so we can get to the question.
Okay, well anyway, that was all I wanted to say.
Good point. It's all of us.
Thank you.
I wanted to interject another theory in this. Just when citizens around the globe, including Siskiyou and Shasta County citizens, have gotten off the chart levels of aluminum and barium, we're talking probably about 80 tests at certified EPA in Reading. We now know that Fish and Game has dropped aluminum from their testing after decades. We now know that all water resource boards in California have dropped aluminum, and we find that very suspicious.
I'm sorry to interject, but is there a question? Because
Yeah.
we have
I
limited
want to
time to
ask
speak.
you, are you aware of that?
Nope.
Well, I'm going to send you this, and
Not
I
yet.
hope you deal with it.
So, right here?
Me?
Okay.
You keep talking about prescribed burns, they used to call them controlled burns, and I know in our area, in the Reading area, a lot of controlled burns, burned houses and so forth because they got away. In going over Highway 89 here in past years, the Forest Service let out contracts for equipment to come in, contractors to come in and shred all the underbrush to get away from the fire underneath. Why, and like that picture right there, you're burning. Why don't you think that mechanical equipment and shredding the brush and cultivating the ground instead of burning, you get rid of the smoke? Why wouldn't that work?
Because to me, that's only short term. So what happens when you just slick off the brush, right? Whoop, sprouts right back. Oh, that was effective for
Well, you'd have
5
to do it
years.
over and over, but it's a lot cheaper than spending billions of dollars on fires.
Or I can burn it for $150 an acre.
That's much.
But then we have the smoke.
Yeah. These were called the Blue Mountains, the Great Smokies, and it's tough. That's a huge issue. Smoke is going to go up if we do this. It's going to go up anyways if we don't. That's my prediction. I mean, take that with a grain of salt.
Alan Buckman, are you familiar with Alan Buckman? 20 years Cal Fish and Game.
No, sir.
Alan Buckman spent 20 years with Cal Fish and Game, and I don't know how many years with the U.S. Air Force. He testified July 15th at the Board of Supervisors on the aluminum issue, on the tree issue.
Is there a question here?
Yes, and everyone has their soapbox, but I'm almost done. The question is, because you just told this audience you were not interested in what this lady presented. We have an aluminum contamination issue. It's now been dropped, but if you were to watch that testimony, you just said you were not interested in a tree contamination. Why are you not interested? The question is why are you not? The question is why are you not interested in a tree contamination issue that was just documented by Alan Buckman, a retired biologist for 20 years and a retired Air Force. Why are you not
Can we move on
interested?
to climate change and keep the topic? We don't have a lot of time.
No, I want to answer. Why are you not interested in the tree
You can speak with
contamination?
him after about that particular thing.
Please, let's stay on
So,
topic.
could I get the next question, please?
Thank you for the answer.
I'm curious about those figures you came up with on the proactive versus the reactive. Are those for the public sector primarily? Are those pretty solid figures? Are they rough? Do they apply to the private sector?
They're pretty fudged, and they're specific to what I deal with the agency. So if you look at Forest Service expenditures, it's specific to that.
I have a question about all those piles of trees and brush up Old McLeod and also along 89. It looks as though those were done for thinning purposes and also, I guess, some log sales. What's going to happen to that? Is it going to get chipped? And secondly, isn't that preferable to doing all this emissions by burning?
Yeah, it definitely, if they will burn it, because imagine that was all piled up, it's either rotten on the inside, so you can't really make boards out of it. Now you have a bunch of rocks and dirt in there, so you can't throw it through a chipper. So yeah, you would end up burning that stuff. But the reason why they happened in the first place, if I think I know what you're talking about, was a huge black stain in the noses root disease issue.
What?
Root disease.
Oh.
And so that was one of the methods to kind of quarantine that area so it doesn't spread any further. What they found is they monitored that over time, it kept expanding, so they finally got to it, knocked it down so that hopefully it doesn't expand. And as a consequence, you do have some material left behind that needs to be rid of.
How important would you rank having markets for unmerchantable wood spread all over the place in forested communities for utilizing unmerchantable wood? Doing your pre-commercial.
Say that one more time.
Having a market for it, biomass.
That would be awesome. I mean, I've heard of this pyrolysis machine that is supposed to be coming online, which is technology from World War II, and I get to see it. Right? It's supposed to be this awesome trailer you throw out to 10-inch chip or wood in there, and out comes diesel. No, biochar is like
If our climate's getting warmer and drier, why would West Nile virus get out of control? I mean,
I just found out the West Nile virus wasn't local, it wasn't native, so I don't know.
Maybe that's something you can answer.
I'm not sure they understand exactly why. It may have something to do with the mosquito, because it wasn't just drier, it was, if it's drier and there's more seasonality to the rain, it might have something to do with the mosquito, but it also might have to do with the transmission from the mosquito to the host, that somehow the virus is better at getting out of the mosquito in warm temperatures. It's not well understood yet. These are pretty new
because I know the
studies.
mosquitoes are, since it's been so dry, have been a lot less this year. So
Right, but
things get drier and warmer, I don't know why. And why, precipitation is so much lower, and why is it being so out of control like the Hampshire?
It's a matter of what time of year the mosquitoes are breeding and transmitting the virus versus the time of the year when the precipitation comes in. So, I mean, if we had no precipitation whatsoever, probably we wouldn't have mosquitoes and it wouldn't be a worry. But if we do get a pulse of precipitation at one point, and it's at the right time for mosquitoes to breed and transmit the virus, that's what it's likely to be.
Thank you.
Yeah, I just wanted to ask, I think that what they were referring to was the, weather modification, and I don't know if that would even be something that the forestry would even be concerned about, but there's been big proposals, for future.
Modifying weather?
Yeah, there's been proposals at the UN, and there's a book that's
We're talking
coming
about
out.
sea clouds and
Yeah.
contrails? Is that what we're
Cloud
going?
seeding, yeah, there's a book just
That's
came
why,
out.
that's why I want to discuss
We've
this.
got 2 more minutes, so let's try to keep straight to climate change,
So
which
it's
is
not
why our
something
speakers are
that the
here.
forestry would even be, I'm not saying what's happening
If
now.
it's proven, sure, absolutely, absolutely.
I mean proposals for the future, because they're proposing it as a future solution. Would that be something that would?
I haven't heard it in any conference, any scientific community. I've only heard it in drum circles, to some
Well, in
extent.
San Francisco.
So if it affects the health of the trees, though, wouldn't that be your concern though later on though? I mean,
I'm sorry?
if that proves to be, affect the health of a tree?
Absolutely. And that's a big issue. But prove it. Or show a trend, basically.
I think if you just walked out in the forest, you'd see.
Well, we're talking about something completely different, that cause and effect, you tie those together, and then I'm a believer. Prove it.
This picture you have on the screen, maybe you can tell me a little bit more about where am I supposed to be seeing the gain in that picture? That from the burn part, I mean, it's non-burn part.
Yeah. So, the advantage of that is what is the fire doing right now? What's the intensity? Pretty low. What's the rate of spread? Not that bad. What's the flame length? Hardly a foot. Can you put that up with your boot? Almost certainly. What are the crowns doing? Are they flaring up and turning red and scorching out? No. So if the fire rolled through there, it's a maintenance tool. So you go and mechanically treat, you get prepared for that fire, and you use fire then to maintain that over time, which increases diversity and there's a whole bunch of benefits from that as well.
So this is going to change in the next 10 or 15 years, is that it?
Yeah, it always changes. It's dynamic. It's always changing. Always. Yes, absolutely.
Okay, so we can only go for one more question. I saw a hand over there. And afterwards, you can come up and speak to the presenters if there's a little bit of time, but we'll have to start wrapping up with that.
It seems to me with the summers getting longer, so that by the time you get to July, the ground is really dried out, that leaving carbon in the soil, which, you know, becomes humus, it holds more water, would be a strategy for not only sequestering carbon, but also helping to maintain moisture in the groundwater. Is there?
This guy has a really good.
Doing this right here puts more carbon in the soil over the long period of time than if you were to allow things to rot and have a big, severe wildfire come through and then burn down deep into the soil because of all the humus that's in it. This actually puts more carbon in over time than not doing it.
So just when I'm doing my field production at home, it would be better to just, for me, to just chip the stuff and let it fly than to heavily brush piles and burn it. And just for my own fuel reduction purposes.
I just think of the pile is you're starting to volatilize the goodies.
See, depends on your objectives, totally. What you're doing there. If what it is fire hazard reduction, then you chip and spread it around and have fuel everywhere. May not necessarily be what you want. You want to break it up. No matter what you do out there from a fire hazard perspective, you want it broken up so the fire can't easily just flow across the area, unless it's really low in fuel like this. But if you have chips that deep across your property, that means when a fire comes through, even though the flames may not be going up into the tops of trees, it's hot enough around the base of the trees to bake it and kill it, is basically what you're dealing with. So
these are chips and piles.
You know,
Spreading.
or incorporate it up. You know, there's folks who are doing where they're chipping fuels and then they're coming and trying to incorporate it into the ground. So now if you do have a whole bed of chips, it's not continuous bed of chips. Some of it's in the ground, some of it, I don't know if that's been published yet.
that's what we've seen a lot in the Tahoe Basin, where they don't use fire much at all, and they chip everything, and they end up with these amazing chip beds all over the place. And when they do get fires in there, even though the fires don't get up and get into the crowns very often, except if they have some wind, most of the trees die anyway because of being baked around the base.
So, unfortunately, we're going to wear out our welcome here at the museum if I don't wrap up. So I want to thank our three speakers. Next month, we are partnering with CalTrout to do a workshop on drought, what's been going on in this county, and what we're doing about it. So we encourage you to pick up a flyer if you want and bring it home. Have a good night. Thank you.